everyone. This video I'm going to be looking at the second part of the counters prac, which was the 4-stage counter. And rather than try and build it on breadboard, I thought it would be best to demonstrate this using the circuit wizard simulation. So we're going to make this 4-stage counter here, and here is the circuit diagram. And notice how there's a bit of a modification. So in the previous circuit we had this stage here, which was our debounce switch. Okay. Now that debounce switch is a form of a monostable, meaning it's stable in one state. So when you press the button, that disturbs it, and it goes into a logic high state. But then after a short amount of time, it will revert back to its logic low state and stay there until you press the switch again. We're going to replace that with something that basically automatically does the high to low for us, and it's an astable. So another type of multivibrator called an astable. And so this part of the circuit here is an astable. And then we're going to feed that into a circuit that is made up of these D-type flip-flops, each of which are connected or configured to behave as a toggle type. So connecting this not Q to D makes it a toggle type, and you can see that they are cascaded, and well, the connection's not here, but it should be, where the output of each flip-flop is feeding into the clock input of the second flip-flop or the next flip-flop, and we call that a ripple counter. So this is going to be a 4-stage ripple counter, and you can work out how many different states it has, but it's going to be 2 to the power of how many stages there are, because each flip-flop can have 2 states, so each combination is 2 times 2 times 2 times 2, which is 2 to the power of 4, which is 16. So this will have 16 different states, or a modulus of 16. So let's get started. The first thing we should do is build the astable and just get it working. So I'm going to go to my Circuit Wizard Student Edition to do this. Click on Gallery and Logic Gates and find my NAND gate there. And using Control C and V, just like before, we can get rid of the copy the gates together, and go back to the diagram. We need 2 100k resistors and a 110 microfarad capacitor. Find them under the passive components, resistors. So we have 2 100k's, which I'll change those in a moment, and capacitor, 10 microfarad. And you can see that the input of each of these NAND gates are tied together, and that's connected to that. So this one is connected there, and this was connected to output, and then just each one of these was connected together like so. 10 microfarads, and so that we can actually see the output, I'm going to connect a resistor and an LED. Now I'm going to use the ground connection, zero volt connection. Okay. And just like we did with the previous circuit, we simulated using this play button, run, and something's not working. Okay, it is working. I reckon it's a bit high. So what do we have in the previous circuit? 470. 470 ohms, make sure that's blank. Okay, and it's quite dim, so what I might actually do is just make it a bit lower. 220. Just a bit brighter. Okay. So you can see we have now, without any input at all, I don't have a switch. We've got this feedback set up so that it's producing pulses that occurring about probably once every second or so. And one of the nice things about Circuit Wizard is you can use a probe on here, on the output, to be able to look at the voltage over time. And you can see here, we've got this graph, and it's producing a nice sort of generally square wave. Okay. And it's got a frequency of around about 1 cycle per second. Just so I don't crowd my screen, I'm going to turn off that graph. I can turn it back on again later, and I'll delete that probe. Okay, so build and check the first stage. Now I'm going to add this first flip-flop. And the reason we're going to add just the first one is because then I can just cut and paste that to make it all of mine. So go to 4000 series to find my 4013. There it is there. The first thing I should do is connect not Q to D, and then I'm going to just copy and paste the 0 volt connection to connect my set and reset to them. Okay, and I'm just trying to keep it nice and compact so that it's not too confusing. And just like before, I can put an LED on the output. So I'm just going to actually cut and paste that one up to there like so, to the output there. And now, just line it up a bit. Now we can connect that onto here. And what we should see, just like with the first Prac that we did on flip-flops, whenever this gets a rising edge, positive going edge here, we should see the output change, and because it's set to toggle, this is going to cycle between positive, or to logic high and logic low. Just clearing up some of those things in there and away. Alright, so now if I run the simulator, you can see that it's, whenever this one turns on, supposedly, this one changes. Okay. Look at this, you should see. I think the simulation's glitching a little bit, so in some cases we're not seeing a proper pulse. Yeah, you'll notice that if it doesn't do that spiky bit there for some reason, it's not changing. Doesn't mean to say that it's a faulty circuit, it's just one of the limitations on the simulation. I would actually think that if we were to remove this connection here, so we didn't have to power the LED, this would probably work a lot more reliable. Maybe not. Anyway. Okay, so it usually behaves, but not all the time. Okay, so let's. Now what I'm going to do, if you have a look at this diagram here, you can see that each of these stages here are just the same thing, and they're connected together. So what I'm going to do is just copy and paste the relevant parts, so I don't have to remake every one. And there we go. If you have a look at this diagram, the important thing to notice here is how this clock is connected. So this clock is connected to the not Q output of the previous flip-flop. I connect that to there, that to there, that to there. We should now have our working full-stage counter. Okay. Fingers crossed. Kind of working. There we go. at least it's following the right count sequence. So 1, 2, 3, 4, 5. Skipped one there. Okay. So some of the things that we can do to try and improve this is, let's change all these resistor values to 1. Let's make it 470s. One of the limitations on the simulation is that they use the component maximum values listed, which are usually quite conservative. And so one of the things that they say with the output current is that it can only provide a certain amount of current, and the reality is that it usually can provide much more than that. So let's make that 470. So we're really just looking for whether it's bright or not. That seems to have hurt. No. Come on. Still a bit sort of fussy, but we can sort of see that behaviour we would expect to see. There we go. And okay, that's a full cycle. And you can see that we've got the count. This one changes most frequently, so this would be a least significant bit, and this one changes least frequently, so this would be our most significant bit. Okay. And you can see that this one changes every pulse of this, well, supposedly every pulse. This one changes every second 2 pulses. This one changes every 4 pulses. And this one changes every 8 pulses. And so they are the weightings of these LEDs. So every pulse, this is our 1s, 2s, 4s, and 8s. So we can sort of model this behaviour here with a truth table or timing diagram. It's pretty easy with this table here. And so what we would see here is that we would start at 0, 0, 0, 0. So 0, 0, and that's giving us our binary number, a decimal number of 0. Okay, it has a hexadecimal value of 0 as well. Now Q1, this is the first output. That was the one changing most frequently. This one changed every pulse. So every pulse is a new line on this. Okay, so these are the stayed at 0 for that first one. And that's our decimal 1. Okay, then this one changed, and this one changed as well. Okay, this one stayed the same, and this one changed. Okay, so this one will correspond to 0, 0. They all say like that. So 0, 0, 1, 0. That's a 2 binary. 0, 0, 1, 1 is a 3 decimal rather. Okay, and you can see that if you follow the pattern here, this one changes every 1. So let's just complete this column by looking at this pattern 0, 1, 0, 1. So it's just going to continue in that pattern. And if you have a look at this column here, you can see that it goes 0, 0, 1, 1. And then if we looked at the next pattern, the next one, you would see that this changed and that stayed at 0. Okay, so we've got these 2 zeros and 2 1s, 2 zeros, 2 1s, 2 zeros, so This one, 4 zeros, and, well, you guessed it, 4 ones. And finally, this one is 8 zeros, then 8 ones. See the patterns forming here is that this one changes every pulse, this one changes every second pulse, this one changes every fourth pulse and eighth pulse. Okay. You may also notice that this one changed when this one went from a 1 to a 0. This one changed when this one went from a 1 to a 0. See that pattern forming there? And in fact, this is the key to how this works, is that the output of this flip-flop is determining when this one changes. In decimal, we would count this just sequentially, so 5, 6, and so on, up to, and this would be 15. There. Okay. And then back to 0 again. And in hexadecimal, which is just a way that we could represent numbers up to 15 with single characters. So this would be the same as the decimal up to 9, which 9 is there. Okay. Then this one, instead of writing it 1, 0 for a 10, we write it A, B, C, D, E, and F. And then we go back to 0. So you can see here that with decimal, we can only represent 0 through to 9 with a single character. In hexadecimal, we can represent 0 through to 15 with a single character. But we use the first 6 letters of the alphabet as a capital. Okay. So the weighting or place value of each output, so the Q1, they just correspond to 1s, because each time this changes, it just adds 1 to it. Q2, second one, well that's twice the value, so it's 2's, Q3's out of 4, the weighting of 4, Q4 weighting of 8. Okay. So you can see here, like 10, which is 1, 0, 1, 0, we've got an 8 plus a 2 is equal to 10. Okay. Which is A in hexadecimal. So, the count of the circuit, we talk about count as being the range of numbers that it can represent, or range of values. And so in this case, the count, the lowest was 0 and the highest was 15 in decimal. So we can refer to this in decimal if we like to. We could say 0 through to F if we wanted to use hexadecimal. And the modulus of the circuit is how many different states it could have, which is 2 to the power of 4. So let's actually write that. 2 to the power of 4, which is equal to 16. Okay. We use hexadecimal because we can represent binary digits of up to 4 bits with a single character. And in computing systems, it's just a convenient way of representing binary data. The timing diagram, you'll notice that when we went from the clock went from a 0 through to a 1, this is when the first output changed. So when this LED turned on, that's when this one changed. Okay, and so if we start our timing diagram with 0, 0, 0, like that. So there's there's their initial state, 0, 0, 0. After the first clock pulse, this first one changed. And remember, it only changes on this positive going edge here. It will not change on this one, so it stays there until the next positive going edge, then it changes. Basically, just like we had before with the two-stage counter, you can see this kind of behaviour. Okay. So I'm lining up these transitions here on Q1 with the positive going edge of our clock. Oops. I'm drawing this with the mouse, so it's a bit awkward. And you notice that, so we've got this is going to be a 1, this state is 0, this state is 0, 0. Okay. When this one went from a 1 to a 0, this one changed to a 1. Okay. Didn't change again until we went from 3, which is at this time, to a 4, which is now. So that's when this one changed. So this one, you can see this the change here lines up with the falling edge of Q1. And that makes sense when you look at the diagram, because the clocking input of Q2 here is connected to the not Q of the first gate, so not Q1. So when Q1 goes from low to a high, not Q1 goes from high to a low. Likewise, when not Q1 goes from a high to a low, not Q1 goes from a low to a high, which is what causes that second flip-flop to change if it's connected to that, if its clock input is connected to that. So when we're looking at these here, we don't care about when Q1 goes from a 0 to a 1, but we do care about when it goes from 1 to 0, because that's when it's going to change. So these are going to line up with the falling edges of Q1. Okay. And by the same logic, Q3 is connected in the same way as Q2 is, and so it's going to change only when it gets to the falling edge of Q2. And Q4, same deal. Okay. So that one changed there. I think we run out of space on this one. That would make change there, that would not change there, and that would not change there, so no change on that. Okay, so it actually see the full cycle on this table. Okay. Okay, so this is a ripple counter, but if we wanted to make it so that we had all of the outputs change at exactly the same time, there are circuits that do that, and they're called synchronous counters. The synchronous counter typically uses logic to determine each flip-flop's next state, and all of the clock inputs are connected together. So you can recognize a synchronous counter if you're seeing it as a circuit diagram, because the clock inputs will all be connected together. So if we look at a diagram like this, you can see that the clock input of this one and this one aren't connected together. If they were connected all together the same way, then we would see that they're going to have the same, they're going to change it pretty much exactly at the same time. Whereas in this circuit, they're not going to change it exactly at the same time, because this one needs to wait until the output of this is changed, which takes a little bit of time from when it sees that, that positive going edge on that clock input. So if we have all of the clock inputs connected together, and we have the inputs of this using determinable logic, then that would be a synchronous counter. Now, quite often you can buy synchronous counters as an integrated circuit, and in fact I believe the 4511 that you'll be using in the next Prac is a 4518 rather, it is a synchronous counter. It is also a decimal counter, meaning it counts from 0 through to 9 rather than this counter, which counts 0 through to 15. So it would have a count of 0 to 9 and a modulus of 10. Not like this one. How would you see whether the outputs are synchronous? Well, you could try and connect logic gates to it. That would be quite difficult to actually see though on breadboard. But if you had a large enough flip-flop ripple counter, so instead of having just 4 stages, if I had like 16 stages, that would have 16 times that propagation delay, and I might be able to trigger a logic gate to behave erratically on this one.